For the first 3 years, we were manufacturing our substrates here, and then we tested them in the field. But then it means that you have 1 year to prepare materials and then one chance to try and see how they work. In order to save time, save money, and be faster, I was trying to find a way, how can we do this here? So I was talking to people in Set Aquarium in order to see if they could provide some larvae so we can test our materials at different times in the year, prepare materials that we know that they are gonna work, and then prepare a biggest analysis in the field. So then I met Shale at Set Aquarium, and he had a collaboration with SeaWorld in Orlando. He put us in contact, and then I asked, hey, is there any chance that you can provide larvae and ship them to us so we can test our materials here? And he was like, well, it sounds good. I like the project. How many larvae do you need? And I said, well, like 4,000 larvae would be ideal. And he was like, what if I give you 8,000? And I was like, that would be even better. So they basically use same methodology as we have done in Curaçao to collect the gametes, but then they put all these larvae in water bottles, basically, and they basically ship the water bottles full of larvae all the way to here. And then as soon as we get them, then we have to start our experiments. So we just got the larvae, and then we place them with the new artificial seawater in order to give them a relief because they were in a bottle for at least 18 hours. 3, 4, 5, 6. And now what I'm doing, I'm counting them. The design of the experiment is like basically we want to put 100 larvae in each of these cups. They are animals and they know when the conditions should be proper for them to swim and try to find a substrate to settle. So imagine that they are in the ocean and there is a big storm. They are going to conserve the energy in order to pass through the storm, and then once the storm is gone and the water or the ocean is calmer, then they can swim down and try to find a proper rock. So I would say that maybe the transportation was a bit disturbing for them. And now that they got here, they are still resting. And then from now to a few hours, they probably will start swimming and trying to find a proper spot for them. Also, the temperature in the lab here is too cold for them. So that's maybe why they are even slower swimmers than usual. But I don't think that they are gonna die because of the cold. And then we have different cabinets with controlled temperature, and we will place them as soon as we finish. We've been trying different materials, mainly based on calcium carbonate, which is very hydrophilic. And then when I put it in a container, which is a plastic cup, most of the times, not always, we will see more settlers on top of the plastic rather than on the substrate, because the plastic itself is polycarbonate, and that has a very high hydrophobicity. It's also smoother. The surface is less rough. After they settle on the plastic, it's very easy for them to peel off, and then they die because they are not attached to anything anymore. Then we add some additives to this coating that gives the hydrophobicity to the substrate. We put something that is called TBP, tetrabromopyrrole. It's an organic molecule that is known because it triggers the metamorphosis of corals. As soon as they reach this TBP, it suddenly triggers the metamorphosis of the larvae into a polyp. So we have a coating that not only has this physical property, which gives more hydrophobicity, but also something that triggers metamorphosis. So as soon as the larvae gets there, it will smell the TBP and then pop as a new settler. And then if you compare settlement in the bare substrate and settlement in the coating, it's much better, the coated one. So we are in a good track. So larvae, depending on the species, they can be from 200 microns in diameter all the way to 1 millimeter for some brooding species. But the ones that we are working with, they are like 300 microns to 450, 100 microns.
Let's say during the last 30 years, with the advance of many microscopic techniques and spectroscopy techniques, there has been an advance in understanding how corals form. Now, what it is not that well understood and known is this process of the beginning of the life of the coral, how it forms. There is not much done in that direction because the corals are very small and you get into the limitations of what you can resolve in an amazing laboratory like the Materials Research Laboratory or Beckman Institute. And the advantage that currently we are benefiting from is high energy techniques like synchrotron techniques that can go to a much smaller scale, and that is enabling us to understand much more how these corals form. For example, now it is known how the process is of the formation. It starts with an amorphous particle, it goes into a crystalline mineral. This is, I think, at this point quite well understood. What it is less well understood is how environmental factors can impair or can affect that process, and how much. And that's important because I mentioned before that there is acidification of seawater, there is high temperature. Can these essentially dissolve the mineral? So all that is not well understood yet. So how much can environmental factors influence how corals form?